Hi all, I'm Dr. S. Suresh from the Department of Physics. Today I'm going to teach on the topic nanomaterials. It's a huge topic, but I'm going to cover as much as possible. The contents which I'm going to teach in this part is: first, I give a brief introduction about nanomaterials. Second, I'll discuss on the surface to volume ratio. Surface to volume ratio, which is very important for a nanomaterial. So if you want to understand what is the why nanomaterials are so special, you need to understand what is surface to volume ratio. Otherwise, you can't learn nanomaterials. And third, we see the types of nanomaterial. And fourth, I'm going to talk about the synthesis of nanomaterials. Under synthesis, specifically, I'm going to talk on the ball milling method. And second, sol gel. And specifically, sol gel, I'm going to use it for the synthesis of thin films. And finally, I'm going to talk on the co-precipitation technique. If possible, if time permits, I also wish to give some brief idea about sonochemical method. So these are the content which I'm going to speak in this part. To begin with, first I'll talk about the introduction part. So what are nanomaterials? So if I ask this question, at least a few years back, nobody will say about what is nanomaterial, right? But nowadays, everyone are well aware of nanomaterial. Even a common man can say what is nano. After the introduction of Tata Nano, a common man can say nano is something small, right? So we people, we are education, right? Students, some students may say that as the nanomaterials are particles in the nanometer range. Okay, so some people will say that the nanomaterials are particles in the nanometer range. So this is a statement given by many students. Many students used to give this statement whenever I ask this question. So what is a nanomaterial? What are nanomaterials? I will get a reply. Nanomaterials are particles, right? Particles in the nanometer range. So is it right? Is it right to state in this manner? Right? So of course, partially it is right. The nanomaterials are the particles which having a particle size in nanometer range. But what is that range? Many people will miss this part. So what is the range of the particle size? The range of the particle size, for example, if I say 1000 nanometer, is it a nanoparticle? Can we claim this as a nanoparticle? Definitely not. And what the range? What is the range? The range to be mentioned. Okay, the range is only if it is between 1 to 100 nanometer, we say it is a nanomaterial. If the range is beyond 100 nanometer, we cannot claim that as a nanomaterial. So nanomaterials are particles which have a particle size between the range 1 to 100 nanometer, right? So what is this? This 1 to 100 nanometer, it is the particle size. Particle size. If the particle size is between 1 to 100 nanometer, we can claim that as a nanomaterial. Otherwise, it is not a nanomaterial. But few scientists, they are considering 200 nanometers or more than 100 nanometers, right? 200 nanometer, 600 nanometer. So these are considered as nanomaterials by few scientists, but it is not right. Okay, though they claim in some of the research paper, you can see that the 200 nanometer is used as a nanoparticle. They claim that as a nanoparticle, but definitely not. So what is universally accepted so far is if the particle size is between 1 to 100 nanometer, that is nanomaterial. Otherwise, it is not a nanomaterial. And the nanomaterial, if you have the particle size less than, right, if you have a particle size less than, right, 50 nanometer, right, if the particle size is so less than 50 nanometer, if the particle size is less than 10 nanometer, if you have a comparison of a particle size of having 1 to 100 nanometer, 150 nanometer, 10 nanometer. So if it is greater than 50 nanometer, which means if it is around 100 nanometer, right, that shows some special behavior. And if the particle size is reduced less than 50 nanometer, it shows a different behavior. And when it comes to 10 nanometer, it shows completely a different material. And these materials are called as quantum dots. Quantum dots, right? I hope you might have heard about this word, quantum dots. But many of them, they do not know what is quantum dot. Quantum dots are nanomaterials which have a particle size less than 10 nanometer. If the particle size is less than 10 nanometer, we can say it is a quantum dots. And like that, if you say the 1 to 100, in 1 to 100, if it is greater than 50 nanometer, that is a different material that shows some different behavior. And when it is less than 50 nanometer, some nanoparticles can show some excellent behaviors, excellent chemical property or magnetic property or optical property. Every property will change. And if it is less than 10 nanometer, that is something special which have more pronounced optical behavior, more pronounced electrical behavior, and more pronounced magnetic behavior, etc. So today we are going to learn about the special materials which make our world, right? The miniaturization is possible only after the invention of nanomaterial. So once we might have seen a computer of huge size, but now it has brought to a pocket size computer. How this pocket size computer is possible only due to the nanomaterials, the technological development in nanomaterials, nanoscience, and nanotechnology. So if without nanotechnology, we couldn't have a pocket size computer. We are going to learn about the special materials and why it is special, which makes them special, right? Why it is special and which makes them special is the surface to volume ratio. Okay, so many of you might have asked this question: why nano are something special? What makes them special? So the answer lies in this topic: surface to volume ratio. Surface to volume ratio. So if you learn what is surface to volume ratio, definitely you will get an idea why the nanomaterials are special. The nanomaterials are special because of the surface to volume ratio, right? So what do you mean by surface to volume ratio? For example, let me consider an atom. Let me consider some material, right? Some material having a radius of r. Some material having a radius of r. So what is the surface area of this? The surface area will be 4 pi r square, right? So surface area. So, and if you take the volume, right? If you take the volume of that particular material, right, with a radius r, we can write 4 by 3 pi r cube. So this is the volume. The ratio between this is surface to volume ratio, right? The ratio between this is the surface to volume ratio. And what you get? What will be the answer? So you get the 4 will get cancelled, pi will get cancelled, and so this is r square. So 1 r will be there in the denominator, and this 3 will go to the numerator. We get 3 by r. So 3 by r. So if you consider the material as pure, we can get it is 3 by r. But always the material cannot be sphere, it can be of different sizes. So if it is different sizes, we have to substitute corresponding surface to volume, right? What will be, for example, if it is a cube, for cube the surface area is 6a square and the volume will be a cube. But as I consider, for simplicity, I consider the material as sphere, and right, and I come up with the answer 3 by r. So what do you mean by this? If I give some numerical value, we can able to understand. For example, if r is equal to 1 meter, so let me take r is equal to 1 meter. So what I get? I'll get the surface to volume ratio, right? Surface to volume ratio as 3 by 1 meter, which is equal to 3, right? And if I give r is equal to, right, instead of 1 meter, I give 1 centimeter. I give it as 1 centimeter. So surface to volume ratio is 3 by 1 into 10 power minus 2, which is equal to 3 into 10 power 2. So see here, when you reduce the particle size, so what do you mean by that? So 1 meter means 1 meter is the radius of this. If I decrease this to 1 centimeter, if I decrease this to 1 centimeter, so 1 centimeter, what is happening? The surface to volume ratio increases, which means more surface when compared to the volume. So if I give r is equal to 1 micrometer, I hope you know what is micrometer, right? Which is 10 power minus 1 into 10 power minus 6 meter. So that is micrometer. If I substitute that value, you get surface to volume ratio as 3 divided by 1 into 10 power minus 6, where minus 6 goes up, we get 3 into 10 power 6 as the surface to volume ratio. Okay, like that the surface to volume ratio greatly enhances even if you go to micrometer. And when you go to nano, right? So for example, instead of that, I'll take 1 nanometer, right? If I take 1 nanometer, what I get? Surface to volume ratio is equal to 3 by, so 1 into 10 power minus 9, which is equal to 3 into 10 power 9, right? 3 into 10 power 9. So see here how much greatly it increased to, right? The surface to volume ratio greatly increased, right? So because of this increase in surface to volume ratio, what happens? So it is understandable that as the particle size decreases, right? So what do you mean by that? The particle size, initially the particle size is huge, 1 centimeter, and next I take 1 micrometer. I couldn't draw a micrometer size particle. For example, I drawn smaller, which is 1 micrometer, right? This is 1 micrometer, 1 mu m, and when you go to that nano range, it will be even smaller, which is 1 nanometer, right? So like that, as the particle size decreases, the surface to volume ratio increases. So what do you mean by that? So because of that, what happens? Okay, simply I'm saying that surface to volume ratio is the reason. What do you mean by that? To understand that, first of all, you must know the difference between what is surface atom and what is the bulk atoms, right? So we know in materials, if you take any material, right, the atoms can present in the bulk, right? Atoms can be stacked like this. The atoms can be present in the bulk. The atoms can present even in the surface. But the surface atom is not same as that of the bulk, right? So if I have some surface atom on the top, right? So what is the difference? The surface atoms, it is not covered by atoms in all the directions, right? So if you take a surface atom, so for simplicity, I'll draw here. I'll take a surface atom. This surface atom is surrounded by adjacent atoms will be there. There will be a definite bonding with the next adjacent atoms, and there will be bonding with the below atom, or it may be right. So if I take this direction, the horizontal direction. In horizontal direction I'm speaking. So this horizontal direction. In horizontal direction 4 atoms, in the bottom there can be 1 atom. And the top there is no atoms, right? So the top there is no atoms. However, if you take some atom in the bulk, right, any atom in the bulk, that atom is covered by atoms in all the directions, top direction, right? So top direction I draw with a different color to indicate that it is the top atoms, right? The side atoms, the bottom, in all the direction it is covered with atoms, and they do have a bonding between all, right? The bonding will be there between all. If I have to remove an atom from the bulk, I need more energy, because the number of bonds to be broken will be larger. So if the number of bonds to be broken to be larger, then I need more energy. But if I need to break an atom from the surface, I need less energy, because the top direction there is no bonding. So the energy, it is already possessed in that atom, right? So whatever the additional energy which is required by the bulk atom, it is present as a potential energy in this atom, right? The additional energy is present as a potential energy in this atom. This potential energy will be much larger for the surface atom, and this energy we call that as the surface energy. So the atoms present in the surface will have an additional energy called surface energy, because it is not covered by atoms in all the directions. So if there are more number of atoms at the surfaces, definitely it have some excellent behavior. So that is the reason. So you can see here, when you compare to the particle size, right? As the particle size decreases, the surface, there are more surface when compared to the bulk, which means more number of atoms present in the surface rather than the bulk. So that makes them the nanomaterials special. And for a comparison, if you take a nanometer, right? If you take a 3 nanometer size, if you take a material of 3 nanometer, for a 3 nanometer particle, there will be 50% of atoms in the surface, right? 50% of atoms in the surface. And if you take something around some 10 nanometer, right, there will be 20% in the surface. And if you go for some 30 nanometer, near about only 5% in the surface, right? 5% of atoms in the surface. So as the particle size reduces, you can see the more number of atoms in the surface, and if more number of atoms in the surface, definitely it will have a very high surface energy when compared to the bulk material. That is the specialty of nanomaterials. That's why the nanomaterials are special. That makes them a special material when compared to other, right? So which gives all the behavior. So whatever the behavior, right? For example, you can talk about the optical behavior, right? Or optical properties, right? Chemical properties, its mechanical properties, and magnetic property, electrical, catalytic, antimicrobial. So like that we can tell, right? We can tell many such properties, right? Almost all the properties can vary. It depends on what kind of material we are taking, right? So we cannot say every material can exhibit every such behavior. For example, if I take Fe2O3, then I can talk about magnetic behavior, electrical behavior, right? magnetic behavior and electrical behavior, and catalytic and few other properties also can be added to it. But if I take zinc oxide, ZNO, so ZNO cannot exhibit this magnetic behavior, right? Magnetic property cannot be exhibited by ZNO. So in common, I listed out all the properties, but different materials, right? Different materials can exhibit different properties, right? And depend on what kind of material we have chosen, we can talk specifically on that behavior, okay, or specifically on that properties. So I hope you had a clear vision about why this nanomaterials are special, right? It is special because of the surface to volume ratio increases, right? So even I can give another example to tell about this surface to volume ratio, all right? Surface to volume ratio. To make a comparison, small comparison, I can tell another example, right? So where consider a material, so a cubic material with side is 1 meter. So let me consider it as a 1 meter, right? And if I cut this into, right, 8 spheres, right? I can cut this into 8 spheres, right? So like that, I can, okay, the diagram is not very much clear, but I hope you can believe that 1, 2, 3, 4, like that, I cut this into 8 spheres. If I cut it into 8 spheres, the side is divided into 1 by 2, right? It is 1 by 2 meter. And we know for a, right, for a sphere, that means, I'm talking sphere, sorry, for a cube, I'm really sorry. If I take this cube, right, so for this cube, it is 6a square, right? 6a square with side length a is the formula for the surface area. And for convenience, I took 1 meter. So if I took 1 meter, the volume is 1 meter cube. In every single case, right? In every single case, the volume going to be the same. Because I'm not taking any part out of it. All the parts are there. The only thing is I'm just dividing it into 8 pieces, right? So let me consider 6a square, 6 into 1 by 2 square multiplied with how many such pieces are there? 8 such pieces are there. So if it is square, it should be 3 here and it should be 4 here. So 3 into 4 is 12 meters square per 1 meter cube, right? What is the surface area? It is 12 meters square for 1 meter cube. And suppose if I divide this, right, I take that cube and I divide that cube into further pieces, right? Instead of having two, I divide that like this, right? So which means I'm dividing this as right. So I hope you could visualize that. So into three such cubes, So 3 and here 3, like that. If you divide that, so how many cubes will you will be obtaining is you will be obtaining right 6a square. So the side length is divided as 1 by 3 meter square multiplied with 27 such cubes. You will be having 27 such cubes. But the volume is going to be the same because I'm just dividing it, but I'm not taking any piece out of it. So the volume is going to be the same. So and now if you do this, and this will be right, 3 means it is 9, and this will be 2 times. 1 3 will be cancelling this to 9, and 1 3 is 2 times. So 2 into 9 will be 18 meters square. 18 meters square. So like that you can see, but in denominator, right? In denominator it is going to be the same 1 meter cube. It is going to be the same 1 meter cube. So hence this shows that the surface area simply increases as we divide it. And if you divide further to nanometer size, we can get enormous amount of nanomaterial. But the volume going to be the same. Okay, so this is another example to explain what is the surface to volume ratio. Right, now we move on to the next part. So the types of nanomaterial, how to classify the types. So, and there are many confusions in classifying the types, right? So there are many confusions. So let me tell you. So some people, they are classifying the nanomaterial based on, so the classification, they classify based on how many dimensions, how many dimensions within nano range. Okay, so they classify like this, and some other people, in few other people, they classify based on classification, right? So classification. Classification of nanomaterials. So they classify based on how many dimensions, how many dimensions outside nano range, right? I hope you can understand what is nano range. Nano range means it should be 1 to 100 nanometer, 1 to 100 nanometer, right? How many dimensions are outside nano range, right? For example, I hope all the materials are three-dimensional, right? So we restrict that to x, y, z, right? So whether the x dimension, y dimension, z dimension, all the three dimensions are within the nano range. That is one classification. The other classification, how many dimension outside nano range. That is the second classification. So many people are, they have excuse me, they have a confusion between these two, right? And which is the best? Which is the universally accepted? Universally accepted. Instead of speaking best, we can say which is universally accepted. The universally accepted is the classification based on how many dimension outside nano range, and this was given by Segal, the scientist Segal. So he said that the best classification of nanomaterials is based on how many dimension outside nano range, not within nano range. And now I'm going to speak the nanomaterials, the types of nanomaterials based on how many dimensions outside nano range, not within nano range. Okay, you have to be more clear about what I'm speaking. Okay, so classification of nanomaterials. Nanomaterials. So that can be classified into four. So one is 1, 2, so 3 and 4. Okay. The first is zero dimension. Zero dimension. So zero dimensional nanoparticles. The second is one dimensional nanoparticles. The third is two-dimensional nanoparticles. And the fourth is, I just extend this to certain extent. So this is three-dimensional nanoparticles. So three-dimensional nanoparticles. Like that, we can classify the nanomaterials based on the how many dimensions is outside nano range. Outside nano range, one-dimensional, zero-dimensional, one-dimensional, two-dimensional, and three-dimensional. So first to see what is one-dimensional nanoparticles. So one-dimensional nanoparticles means all the three dimensions are, right, sorry, how all the 3 dimensions are outside, yeah, right, outside nano range. Sorry, not all the 3 dimensions, none of the dimensions. Sorry. So we are talking about 0 dimensional, 0 dimensional. So none of the dimensions, none of the dimensions are outside nano range. None of the dimensions are outside nano range. So you can clearly see that it is 0, 0. No dimensions is outside nano range, right? Which means that all the x-axis, y-axis, right? For example, if I draw a picture like this, right? So here I'll draw separately. So to be more specific, we can say it is x, and this is y, and this is z, x, y, z. So x is in 1 to 100 nanometer, and this is 1 to 100 nanometer, and here also it is 1 to 100 nanometer, which means none of the dimension is outside nano range, which means that it is not greater than 100 nanometer. That is the meaning, right? And this is 0 dimensional nanoparticle. Example, quantum dots, right? We learned what is quantum dots, right? Actually, nanopowders, nanopowder, fullerenes, quantum dots. So these are all example for 0 dimensional nanoparticle, 0 dimensional nanoparticle. And what is 1 dimensional nanoparticle? What is a 1 dimensional nanoparticle? As the name indicates, one dimension outside nano range. So pictorially we can draw like this. So x, y, z. So one dimension alone is above 100 nanometer, which means let us consider this is 1 to 100 nanometer. This is 1 to 100 nanometer, and this is greater than 100 nanometer. If something is greater than one dimension is greater than 100 nanometer, we can say it is 1 dimensional nanoparticle. So which was the example, right? So example is nanotubes, nanotube, right? Nanowire. If in the form of wire, if it is in the form of tubes, right? For example, tube means if you draw a tube like this, length alone is outside nano range. So this length is greater than 100 nanometer, whereas the other 2 dimensions, right? It's the other 2 dimensions are within 100 nanometer. It is 1 to 100 nanometer. So like that, the other 2 dimension means its thickness. So it is in nanometer range, and it is above 100 nanometer. If it is above 100 nanometer, we can say it is 1 dimensional nanomaterial. And 2 dimensional, so 2 dimensions, right? So 2 dimensions are outside nano range. So what do you mean by that? So pictorially we can draw like this. So we can mark that. So this is 1 to 100 nanometer, and this is greater than 100 nanometer, and this is greater than 100 nanometer. Then we can say it is a 2-dimensional nanomaterial. So what is which one is 2-dimensional nanomaterial is? So thin films, nanosheet, right? Nanosheets. We can say nanosheet or thin films, right? Thin film or nanosheets. So these are some of the example for 2-dimensional nanomaterial. So here in this case, the thickness alone in 100 nanometer. The thickness alone in 100 nanometer. This is greater than 100 nanometer, and this side is greater than 100 nanometer. The thickness alone in the case of in the range of 100 less than 100 nanometer or 1 to 100 nanometer. So that is this is for the two-dimensional nanomaterial. That means the two-dimensional nanoparticle where two dimensions are outside nano range, and three-dimensional nanoparticle, all three dimensions, all the three dimensions are nanomaterial. That means outside nano range. All three dimensions. All three dimensions are outside nano range. Outside nano range. So which is bulk material. So this is our, simply we can say it is a bulk material, right? So bulk material. So it is actually not a nanomaterial. It is actually not a nanomaterial. It's a bulk material. So this is the classification of nanomaterials based on how many dimensions outside nano range, and this is the best way of classifying the nanomaterials. Okay, and best way, even we can say it is a universally accepted way of classifying the nanomaterials. Now we move on to the next part. So how to synthesize the nanomaterials? How to synthesize the nanomaterial? To synthesize nanomaterial, there are two major approaches there, right? Two major approach. The first one is top down, and the second is bottom up, right? There are two major approach to synthesize a nanomaterial. So synthesis of nanomaterials. Right? So there are two major approach. One is, right? So one is top down approach. The other one is bottom up approach. Bottom up approach. There are two major approach of synthesizing nanomaterial. So first, let me talk about what is top down. What is top down approach, and what are the advantages, and what are the disadvantages. Everything I speak related to top down approach. So when you talk about top down approach, top down from bulk material, from larger material. For example, if I take a bulk material, right? And if I crush the bulk material, right? Crush, so mechanical deformation. So if you, for example, if you have a brick and if you hammer it to pieces, right? So that is like a top down approach. From a larger material, you are bringing to smaller powder, right? So this will be divided into few, right? Few particles, and this what is the, right? So I drawn different sizes, right? Different sizes. So what does it mean? When you break using even a brick, if you break it using a hammer, you can't have a uniform size. Uniform particle size is not possible. Different sizes are will be available, right? Even there will be certain powder. Even that powder may be in nanometer range. Who knows? So like that. What is the biggest disadvantage of this material is also that we can't get a uniform particle size. Okay, and if it is broken to pieces, and again, if it is uneven, again we tend to break it, and if you tend to break it, and we bring up to nanomaterials, right? So this may be some bulk material, and this may be, again it is in it may be in some bulk, this can be in something around micron size, and this is nano. So like that, if you come up with nano simply by mechanical deformation, okay, and the way how we bring it, there are many different methods are there, right? Many different methods are there. So for example, so ball milling, so ball milling method, right? And gas phase condensation, right? And apart from that, so lithography, electron beam lithography. So like that, there are many different techniques are there. There are many different techniques are there through which the mechanical deformation can be done and brought to some very fine nanoparticle. Okay, so many different methods are there, but the best used is ball milling method is the best used among this, and that's why we are going to learn about what is ball milling later on when I explain how to synthesize the nanomaterial specifically. So I'm just talking about the overall approach, and after that I'll teach one by one. So here, from large material we come to a small powder. So what are the advantages and disadvantages? What kind of disadvantages here? The first one, right? First one, we here the uniform particle size is not possible. Is not possible. Okay, uniform particles uniform particle size is not possible. What do you mean by that? So for example, even if it go to nano range, even if it go to nano range, if one particle is in 30 nanometer, if some other particle, if it is in 40 nanometer, if some other particle having a 60 nanometer, if some particle having 20 nanometer, is it good? Is it good? Definitely not. I said the particles, right? As the particle size changes, the property also changes. If I have a particle size of 60, which is above 50, that shows a different behavior, and when compared to the one having 20. And even if some particle having 10 nanometer, that is even more poor, right? So that may be the biggest problem in this case. So you may not get a uniform particle size. Uniform particle size cannot be easily achievable. And suppose if you want to achieve that, you have to crush it again and again, and longer duration is required. But still, there may be some different particle sizes. It can be reduced from a greater extent. It can be reduced to a small extent, but the uniform particle size mostly it will be missing, right? That is the first drawback. The second drawback is the starting material. Starting material. If I want to synthesize ZNO nanoparticle, I need to synthesize ZNO, right? I'll write there. So if I want to synthesize ZNO nanoparticles, the starting material is ZNO bulk powder. Okay, that is the starting powder, which means whichever nanomaterial I need to synthesize, the same material has to be taken in order to here we are not doing any chemical precipitation. That means chemical reaction doesn't take place. Simply we bring it to nano powder by mechanical deformation. If you do that by mechanical deformation, then the starting material should be the same material. If I need zinc oxide nanoparticle, zinc oxide bulk powder should be taken. If I need iron oxide nanoparticle, iron oxide bulk powder to be taken. So like that, the same material has to be taken, right? The starting material must be the same material which has to be synthesized, synthesized as nanoparticle. So it should be same precursor. That is also a drawback. And one more disadvantages. So these are all disadvantages, right? Whatever I'm speaking now is disadvantage. So why I'm speaking disadvantages is there are more disadvantage when compared to advantage here. So very less advantage. So let me talk about the overall all the disadvantages, then I'll speak about the advantages. So the third, what is the third disadvantage? The third disadvantage is here this material, right? So there is this approach. In this approach, there will be many large waste will be there, wastes, right? Because when you crush to powder, you cannot have all the powders. We cannot collect all the powders. That is not possible. More wastage will be there in this approach when compared to the other approach. Sorry, when compared to the bottom up approach. So here more waste, more wastage possible than bottom up, right? More wastage possible than bottom up. That is also a drawback. And you cannot use it for all the material. Some materials cannot be mechanically deformed. For example, if you take iron pieces, and can you crush it and bring it to powder? Definitely not possible, right? That is not that much easy. So you cannot use, and some material, some material when it get heated up, because here when you do some mechanical deformation, there is lot of possibility there where the temperature of the material can increase. If the temperature of the material increases, it can convert to some liquid quite easily. Some material can even vaporize. So it cannot be used for all the materials. Those material which is thermally stable and which can easily mechanically deformed, that materials alone can be used. So it cannot be used for to synthesize all the materials. It cannot be used to synthesize all the materials. It cannot be used to synthesize all the materials. Okay, that is not possible because certain materials can be hygroscopic, certain materials cannot be mechanically deformed easily. So those materials cannot be synthesized using this technique, this approach. So like that we have disadvantages, a lot more disadvantages when compared to the advantages. So when you talk about advantages, so what is the advantage? Advantage of this particular method, right? The main advantage of this material is, so large production is possible, right? So at a time, if you go to bottom up approach, in bottom up approach, the amount of yield, right? Yield means how much nanoparticle we can synthesize at a time. That may be very less when compared to that. Here, large production is possible means yield is high yield. Okay, yield is very high in this case. Yield is very high in this case. That is a major advantage of this material, right? That is a major advantage of this material. And apart from that, the remaining are the disadvantages, right? And it is a simple method. Again, it is a very simple method, right? Simple method, no chemical reaction involved. No chemical reaction involved. So that is also an advantage, right? So if there is any chemical reaction involved, then we need to take care how to control it, right? So like that we may be having right, many limitations are there, how to use it, where to use it, and how to mix it, like that, what proportion to mix it, everything we need to take care. So that is not required in this case. In this case, simply we take it, whatever the large volume we take it, we crush it and bring it to powder. So that is the specialty of this particular method. And bottom up approach. So when you talk about bottom up approach, right, in bottom up, what is the major advantage? Why the bottom up approach is, they gone for the bottom up approach is, the first major advantage is no wastage. no wastage. There is no wastage in this method. That is a major advantage of bottom up approach. So there is a very minimal wastage, or nearly the wastage is nil in this case. Maybe the wastage may arise during the filtration process. So during when we synthesize certain material, it can be precipitated. That when we take the precipitate, wash it, and we filter it, during that time a minimal wastage may be possible, and that too that can be avoided. And nowadays we have very sophisticated instruments are available, how to filter it, how to wash it, and during that time we can avoid wastage, or negligible wastage is possible. That is the specialty of this material. And here, what is bottom up? Bottom up means here it is as the name indicates, atom by atom, right? Atom by atom. Initially, initially we have individual atoms. These individual atoms will combine, right? Combine to form small particles, and that will club together to form materials, right? So here, so this is nanomaterial, this is nano, and this is individual atoms. Individual atoms or molecules. So that will be clubbed. So this is one, this is one. So like that it will agglomerate together. So it combine together to form a nanomaterial. So atom by atom it forms as a nanomaterial. That is the bottom up approach. And most of the nanomaterial synthesis are bottom up approach. Most of the nanomaterial synthesis are bottom up approach. For example, chemical precipitation, right? So sol gel, co-precipitation, biosynthesis, sonochemical. So like that we can just list down all the material methods. The remaining most of the methods are bottom up. Most of the methods are bottom up, right? Only very few methods are in top down approach. Mostly it is bottom up, right? Now I will move on to the next part. So how to synthesize nanomaterial using ball milling technique. So ball milling. So ball milling is, it is an example for top down approach. So ball milling is an example for top down approach, right? Just a minute. So ball milling, it comes under top down approach. Top down approach. So here it consists of a container. It consists of a container, right? A container. And generally this container is made up of tungsten carbide material. This container is made up of tungsten carbide. So why specifically it is made up of tungsten carbide? There is a reason for that, right? Because the tungsten carbide, it is one of the hardest material, right? It is one of the hardest material. So hardest material, and the tungsten carbide, it is non-sticky for magnetic materials. Non-sticky for magnetic materials. Suppose if you are synthesizing some magnetic materials, so what happens is that magnetic particles, some of the particles can stick to the metal, right? And we need a metal which do not stick to magnetic materials, which can easily separate from the container. If it is not easily separable from the container, then what is possible is contaminant can be present. For example, if the first time I synthesized ZNO nanomaterial, if the second time I want to synthesize copper oxide, if I didn't clean up after synthesizing ZNO, the ZNO, some of the ZNO particles can be present as an impurity phase in copper oxide nanoparticle. So like that, there will be certain problem will be arising if you use some other material. That's why the tungsten carbide material is used in most of the cases. And here in ball milling, inside this container, there will be small size balls, right? So like that, there will be small size balls, and this balls, the container will rotate, and the balls inside the container also will rotate, and together, right? So during this rotation, the particles which is taken within this can crush to nanopowder. For example, if I have some particles within this, these particles can crush between the balls and bring it to nanopowder. This is how it is synthesized in a ball milling method, right? And what are the advantages and disadvantages of having this ball milling technique? It is a very simple technique, right? As I discussed about top down approach, it is a very simple technique, just a container with balls, and we take the bulk powder and we crush it to nano material. So easily it can be done. And what are the disadvantages? As I said, it cannot be used for hygroscopic material, right? Hygroscopic materials, or it cannot be used for materials which is not thermally stable. Because during the process, enormous amount of heat energy will be produced, and during that heat, if the material get collapsed, then there is not possible of using this particular technique, right? And it is a time consuming method, right? For example, if you want to synthesize some very fine nanopowder around 10 nanometer, if I want a particle size of 10 nanometer, even in certain cases it may be, right? So even for 24 hours it should be spun, right? So it should be ground for 24 hours or even 30 hours. It depends on what material we have taken. So like that, the long duration, it is operated for a very long duration. If you operate that for a very long duration, heat energy can be produced, which can definitely affect the particle size. That means even when heat is produced, when heat energy increases, the particle size can also grow, right? So we might have studied about what is sintering. Okay, so during sintering process, particle size can grow. So like that, certain drawbacks is there using this ball milling method, and so this is not applicable for all the materials, and it is used for only certain materials, and that too we have certain drawbacks. And next, quickly I just brief about what is a sol gel method. So sol gel method, okay, sol gel technique. So when you talk about sol gel, it is a wet chemical synthesis, right? It is a wet chemical synthesis. It is a chemical route. Actually, it is a chemical route of synthesizing nanomaterial. So it is a wet chemical synthesis, and here there are two parts, right? So one is sol, the other one is gel. Sol, gel. Okay. Sol, gel. And what the sol denotes? The sol means solution. It is short form for solution, right? Solution. Actually, this is nothing but preparing a solution where some colloidal particles present within that, right? So here colloidal particles present, or ions. It is simply as some ions. For example, sodium chloride, if you dissolve into a solvent, what happens? It's split into ion, sodium ion and chlorine ion. Like that, either it can be split, it can be as ion, or it can be some colloidal particles. And what is the starting material taken here is, generally we take metal alkoxide. Metal alkoxides are metal chlorides. Metal chlorides. So this is the material, starting material that is taken for to synthesize sol gel, and the gel, right? What the gel denotes? So gel, it denotes that it is a continuous network. It is a continuous network formed, right, by the evaporation of solvent. When solvent evaporates, what happens, right? So within this we have solute particles, right? So colloidal particles are ions, and when the solvent evaporates, the particles will try to unite, right? It will try to form as a continuous network. For example, I'll expand here. So this will tend to, right, this will tend to form as a continuous network, and through this we can synthesize fibers, nanofiber, nanotubes, and nano powder, and even thin film is possible. With certain techniques, we can even synthesize thin films like that. So here it will agglomerate, it will form a continuous chain in order to form as a particle. Either it may be a fiber, or as I said, it can be varied, right? It depends on what material and how the condition we are altering that plays a part here. So in this case, this is gel, right? This formation of continuous network is gel. And whenever we talk about the sol gel, two main processes happening. What are the processes? The first one is hydrolysis. Hydrolysis, right? The hydrolysis is the preparing of sol. Preparing of sol is hydrolysis, and the second part is polycondensation. Polycondensation. Condensation. This polycondensation, it is nothing but it is the formation of this gel, right? Polycondensation. These two processes happening there, and this will lead to the formation of nanomaterial. And in this case, how it forms? It forms as right, metal oxide. So this is metal oxides or metal hydroxide. So while it forms as a network of particles, how it forms? Either it forms as metal oxide or metal hydroxide. Both are possible. Metal hydroxide, for example, it can be ZnO, right? Or it can be ZnOH twice. So metal hydroxide. Even it form as a metal hydroxide, later on we take this, anyhow we are going to do calcination. Okay, excuse me. So this will be calcined. After getting this, it will calcination will be done. Calcination. So when you do calcination, calcination means heating the material in induction furnace at a certain temperature, like 500 degrees Celsius or 400 degrees Celsius. It depends on what material we have been taken in order to calcine it, and through that we can get nanomaterial in the form of oxides. So oxides can be prepared using this sol gel technique. And I'm going to specifically talk on how the thin films are synthesized. Okay, how the thin films are synthesized. So to synthesize thin film, what we can do? What we have to do is we have to proceed with two processes, right? So two processes can be used. One is the dip coating method. The other one is spin coating method. using dip coating and spin coating, we can produce the thin films using sol gel technique. So in sol gel, we know that we have a sol pot, right? In sol, right, the solid particles are dispersed, not dissolved. Okay, in certain cases it is dissolved, and if it is a colloidal particles, it is dispersed. Like that, in the we take a sol. So this is sol, and from this sol, how we can form thin films? How we can form thin film using dip coating? So let us take a substrate, right? I draw this again. I'll take a substrate. Substrate means over which it is just like a sample holder over which the thin film has to be synthesized. If I have to synthesize the thin film over this material, I take that and I dip that into the solution, right? I dip this, I'm going to dip this into the solution, and after dipping it into the solution, I pull it up very slowly. Right? I pull it up very slowly. So I'm going to pull up slowly. And how it should be pulled up? Pulled up very slowly. Why it should be pulled up very slowly? In order to control the thickness. If I need a nanometer thickness, I should pull up very slowly so that the additional solution will be drained out into the solution. So as it pulled up, there will be certain solution over it, right? This solution will drain into the beaker itself. So in order to drain that solution, we have to pull up very slowly so that we can control the thickness. And later on, what is done is it will be kept for evaporation, right? So this is evaporation. That means the solvent will evaporate. As the solvent evaporates, we get thin film. So this is how the thin film is synthesized using dip coating method. We take a substrate, dip it into the solution, and pull it. As it we have to pull it very slowly so that you can control the thickness, and we have very thin nanomaterial can be synthesized using this technique. So this is dip coating method, and the next is the spin coating method. The second is the spin coating method. So in spin coating, right? In spin coating, it consists of a spin device. So there will be a substrate, and this is a spin device. The spin device is attached to a motor, electric motor, and this is a substrate. This is substrate. This is substrate over which the liquid, that means in beaker we have solute, right? A small portion of the solute is taken into this, right? A small portion of the solute is taken into this, and initially it will be a small portion, right? And later on it is spun. It is spun at certain speed. When it's spun, what happens is the solute particles evenly distributed. That means whatever the solution we have taken on this, it is evenly distributed. So evenly distributed like this, and after it is evenly distributed, we can, right? So we can stop it so that the solvent evaporates. As the solvent evaporates, we can get a thin film. So this is how the spin coating method is done in order to synthesize the nanomaterial. And today for this lecture portion, I have covered what is a nanomaterial, and I discussed about the surface to volume ratio. I had discussed about what is the types of nanomaterial, and I discussed on the two major approach of synthesizing nanomaterial. And finally, I talked about what is a ball milling method, which is top-down approach, and I discussed about the sol gel technique, and which comes under the bottom-up approach, right? So thank you.